Professor Kavita Bala, and she is an assistant professor of the Computer Science Department and the Program of Computer Graphics at Cornell University. And actually, she is not working on the material perception a lot, and she is the computer graphics, and importantly, she has been working on how we learning about the human vision can help computer graphics as well. And also, her recent work on the material database is really important for our field. So I'm really happy to call Professor Kavita Bala.
Thank you. Thank you for having me. So as I was introduced, I am a computer graphics researcher, and I sit mainly in graphics, but a little on the boundary of graphics and computer vision. And what I'm going to talk about is recent work in that space, and if I have time, which I know I'm very late on, I'll try to talk about some of the graphics work too. So these are pictures of materials in the wild, and that's what the title says. And the real world is very complex, full of rich materials that we are interested in trying to understand, right? And that's the goal of the conference, and I can talk a little bit about the research we're doing around this. Our goal is to understand materials with the specific sub-goal of using it then to recognize materials in images, so that's the computer vision problem, and also to create better models to render these kinds of materials so that you can use them in virtual applications to do various useful things in industry. So that drives our directions a certain way because we care about producing images that are indistinguishable from reality if possible, and we want to model materials to make that happen. And so to get an idea, here are, this has all gone a little crazy. Hang on. Yeah, so here are my slides. Thank you. So there are various applications. We're all living in a very camera-enabled world, right? So here are all the devices that you are probably carrying 3 or 4 cameras on you right now. And it would be great if you could walk into a room, say like this one, and this was one of the images from earlier, and recognize that it's a living room. And when I say you will recognize it's a living room, but have the computer recognize it's a living room, recognize the objects in it. But more importantly, a lot of people are working on object recognition. The part that I'm focusing on more is also hopefully recognize the materials that are in the room. So to make that happen, you need a lot of information about the materials that are there in the wild, and that drives one of the motivators for the research we're going to talk about today. Another graphics application, and this is an editing application, is people want to explore different material designs. So for example, they might want to take an image like this, and this is a very graphics application, but designers want to take an image and then change it and see how it's going to look after you make that change. So here are the kinds of transformations you might like to make a couch blue or make a rug blue, and that's the kind of stuff you would also like to enable. And lastly, I talked about modeling and rendering, and here is an example of the different kinds of renderings that people have produced virtually to visualize spaces before they design them. I should mention that this is all results that come out of Autodesk 360 renderer. So this is Autodesk is a company that has a cloud renderer, and the cloud renderer is implemented on an algorithm called Lightcuts that we developed in my group. And it's been implemented as their core rendering engine. And so a lot of people get to upload their models, architectural models, prototyping models for cars and other devices, and they visualize them before they ever produce any physical prototype. And making that a full reality by enabling very rich material representations remains one of the grand challenges. We've done a lot of work on the rendering side. Now we need to switch back to the material side and make that work more with the rendering side to make the next big breakthroughs in this space. So that's where we sit. And so in today's talk, I'm going to talk about basically how do you go about taking the first steps towards doing that. So I'll primarily talk on that top bullet. If we have a few minutes, I'll talk about the material models, but mainly I'm going to talk about creating crowdsourced material databases. And particularly, I'll talk about 2 databases. One is called Open Surfaces, which was presented at SIGGRAPH last year, and the other is Intrinsic Images in the Wild, which is going to be presented at SIGGRAPH next month. The main thing I want you to know, though, is these are completely open databases. They're publicly available. They're browsable, downloadable, et cetera, because we really want the community to take it and run with it and use it for all their applications. Because we don't do all of the research and recognition and understanding and segmentation. We want people who do that to hopefully benefit from this knowledge. And as I said, if I have some time, I'll talk about some work that we've done with TED on translucency perception. So a big motivator for our work is we were thinking about what's the state of the art, and that's had a big impact. And we thought that these object and scene databases like LabelMe, ImageNet, Sun have had a big impact on scene understanding and that side of the world. And we wanted to figure out, and we wanted a similar resource on the material side. And there is some great stuff on the material side. So there's the Flickr material database, ImageNet material, Curate, Merle database, et cetera. So that was a very good first start. But their goals were a bit different from ours because they were very high quality typically, but therefore, as a consequence, if you actually have to measure each material, consequently they were a bit smaller in the size than we were looking for. We really wanted to scale to hundreds of thousands of images if possible, and materials if possible. So that was sort of the main motivation of our work. And starting there, we stepped back and started to think about, so what do we need? We want lots of variety because the world is full of rich material. So we wanted to capture that if possible. We wanted realism, which eliminated just using simulation and computer graphics. What is needed is the title. Oh, sorry, can't help you with that. So this is what we need. This is our wish list. So lots of data for rich variety. Realism. So computer graphics still struggles with getting blemishes and weathering and dirt and all of that stuff, but the real world is blemished and dirty and weathered. So we wanted to capture from the real world, not just go and try to simulate a large set of examples. And the other thing we wanted is we wanted the context in which these materials appear, because typically context has been shown to help in driving better recognition, et cetera. So that was our wish list. And then that led to a set of questions that we needed to answer. Where do you get all this data from that we want? How do you get material information, apart from image information? How do you scale to very high, big sizes? And how do you ensure quality? And I'll try to give you a hint of what we did to achieve a pipeline that actually resulted in a large database. So where to get images from? Well, that's what the title says. And that actually is a problem you can solve in modern times. People are posting more images than we know what to do with on Flickr. And so we scraped 1 million images from Flickr. And just, we did a few simple searches and just got tons of data. So getting image data is not an issue at all. And these are images that people have bothered to put up on Flickr, and they're open. That's because we wanted to use it in an open database. They are covered by the Creative Commons, so anybody can use them. But they're actually really rich, beautiful pictures. So taking these pictures then, how do you get material information from them? So these images, they have what we wanted. They're diverse, they have the context, they're real world. But they have a problem that they're images. So they conflate lighting and geometry and material and camera intrinsics all together. And state-of-the-art computer vision algorithms cannot separate them out, particularly for these images in the wild in uncontrolled settings with random cameras, random lighting, et cetera, out in the world. And we are working on developing those algorithms, but they don't exist now. So we knew we needed to do something here. We had raw data. And the recognition was, well, humans are pretty good, not perfect, but we're pretty good at disambiguating materials and this kind of lighting and geometry conflation. So let's toss humans into the loop. So that led us to crowdsourcing, and this is sort of the symbol. We went to Mechanical Turk, where you can pay people to do simple tasks, micro tasks. And that's great. People are pretty good at judging materials. But that doesn't, of course, solve the problem, because while they're good at judging materials, they're very bad at actually communicating information about materials. So they don't know how to communicate that. We need to train them up. I'll talk a little bit about that. There also is this issue that workers on Mechanical Turk can, with the best of good intentions, make mistakes, so they're error-prone. Some don't have such good intentions, they're lazy, and some have actively bad intentions, they're dishonest, they want to take your money, but they have absolutely no interest in doing your task. And so we have to protect ourselves against that set of errors that'll creep into the system. And so we have a lot of verification techniques that have to be embedded in the system. Okay, so our challenge here is get novice workers to accurately describe material appearance, but particularly we want to have a scalable approach so that we can get 100,000 materials. We want it to be verifiable. It has to be of good quality. I mean, getting garbage, 100,000 pieces of garbage is a whole lot of garbage, but it's not useful. And because we're paying people, it has to be economical to scale. We can't afford to pay $10 per material, because that'll break the bank when you get to 100,000 materials, for example. So that was the goal, and as I said, real-world photographs and using crowdsourcing, that was how we planned to achieve it. So I'm going to give you a brief visual sort of demonstration of sort of what the pipeline achieves. So we start off with images, and we get some context information. So when we say we get from the workers context information like, this is an image of a kitchen, and the particular segment, your material segment you're segmenting out is of a countertop. And then we get a segmentation of that quality. So the worker will go and actually mark out a segmentation of quite a bit of detail. You can see that it removed out the grill and just left the rest of the countertop in. Then we get annotations that this is granite, and it has a certain diffuse properties, certain gloss properties, roughness, etc. And that's the material information. And then finally, going from there, we additionally wanted to do one thing. We wanted to get texture information for planar surfaces. In the case that a surface was planar, we wanted to get a surface normal so that then we could rectify the texture and then create an additional texture database while we're going along. So it's a material surface annotations and additionally texture database when we can get it for planar surfaces. So that sort of gives you an idea of the information that will be in our database when I'm done explaining the pipeline to you. Let me give you a quick preview of the pipeline. So first is we do material segmentation. So you can see here a worker is going in and segmenting out the floor, and they are making sure that they don't capture other pieces of furniture. So it's a very, very detailed segmentation that they give. And that's the first step of the pipeline. Okay, so they draw these very detailed boundaries. The second step is to identify what it is. So we give them an interface where they mark that material, and you can see on the right is a whole set of materials. They say that is wood, okay? So now we know the name of the material. We also similarly get that it's a floor, so we get the object name as well. And then the last two are about reflectance and texture. So the worker now starts annotating the reflectance properties and tell us what's the diffuse color, what's the contrast gloss, what's the distinctness of image, or the roughness approximately of the material. And so you can see that's the segmented material here. And on the blobby, you're seeing a visualization of the parameters that the annotator has picked. And they keep trying to match the two. And when they're happy, they declare done, and they move on to the next one. All right? That's the reflectance part. And then the texture part is the last part. Once they have a segmentation and it's planar, we let them rotate this perspective grid so that they can place the normals such that if you rectify the texture, the lines on the floor will appear parallel. That's a good rectification. Okay? That's the high-level pipeline. All right, so now I'm going to go through each part. Actually, let me pop back a level. So at the high level, these are the 4 big stages. You first scrape all your photos. You label the scene categories. I won't talk much about that. That's actually pretty straightforward. I'll talk about the other 3 boxes here. You segment the materials, you annotate reflectance, and you annotate texture. To segment materials, you first draw the boundaries. The boundaries have to be correct. You have to name the material, and you have to name the object, right? I'll show you a little more how you draw boundaries. The correctness is always checked. I'll just mention that there are a lot of tests in here, and we pay workers to do that, so it adds to the cost, but it also keeps the quality good, and that's an important part of our process. So for drawing boundaries, we first actually went to Label Me and used the Label Me interface. And unfortunately, we got a lot of feedback from the workers that it was too cumbersome. And also, we got really pretty bad quality segmentations. They didn't give us very detailed segmentations like the stuff that you're seeing. And so my student had to go in and add a few other features, and it's described more in detail in the paper, like automatic pan, smooth zoom, et cetera. But once we did that, the workers were happy to do, and then you can correct your nodes here too. They were happy to give extremely detailed segmentations. So an example of how detailed, this is at 10x speed, that's somebody segmenting out a curtain, and they really do a good job of going in and marking out the entire curtain as being one material segmentation. We were very surprised, but it turns out that once we enabled and really improved the UI, our old workers who were quite unhappy were lavishing praise on us, and then they would just sit there and do it almost for free because they really liked it. They enjoyed it. They said that they found it somewhat therapeutic to do this. It was a very intense, but it cleared their brain or something. So we had a few workers who would just come back and want to do this, which was great for us. So we got some beautiful segmentations. I'll show you more later. We were quite surprised by that, actually. This part is pretty easy. Then you name the materials and the objects. So for example, you're quickly going through and saying this is tile, that is fabric, et cetera. And there's a pull-down menu of the materials that are there. We chose 34 materials, classic stuff, and you can go and check on the website, wood, fabric, metal, plastic. We had to do things like created painted walls, so we needed to create a painted category. And the reason we had to do that is if we didn't do that, they were guessing what's behind a painted thing, and sometimes they'll say it's a wood wall, sometimes they'll say it's a cement wall, and we didn't want them to guess. We wanted them to tell us it's painted, I don't know what's behind it. So we had to do some work like that to get a good list that we were happy with. I should mention that first we tried to let free-form entry of material names, and that was a disaster. There were misspellings, there were cultural differences, so they would call the same thing by different names. It ended up being not very good, and choosing just a fixed list, which we would like to expand, worked way better and was rather critical to this part. Next part is annotating reflectance. This annotating reflectance and annotating texture were the two hardest for the workers, and it cost us the most too. So the first thing you want to do when you annotate reflectance is you don't want to work in an image that is actually very contorted in color space and stuff. So we actually try to check, and more is in the paper, whether the image is approximately white balanced by getting some feedback from users about that, okay? Once you throw away the images that are not white balanced, now you need to match appearance, and then once you match the appearance, you check if the color is correct and the gloss is correct. I won't talk about the correct testing steps. I'll just talk about the matching appearance step now. So here's a segmentation right here of tile. And we show the workers the segmentation both in context, so they can see it's a tile, and out of context, so they can focus separately on the material directly. So yeah, that says that. Okay. Now the question was, how do you collect material information? We went through actually various models that we could have tried, and we settled on the word-based, the perceptual word model by Pellicini and Forverda. And the reason is we were actually looked at a bunch, we tried a bunch of examples ourselves, and we also looked at prior work that had been using it for material design. People have argued that actually any word model is about the same, but we found explaining to novice workers, and our workers were from all over the world, we had about 1,500 workers, explaining to them the idea of contrast, gloss, and distinctness of image was actually quite intuitive, but trying to explain to them the physical parameters didn't work at all. So we used these two terms, they got it, we trained them a bit, they'd get it, and then we could use that well. So that was the material. While they're making the edits, where do they do it? We have to show them a shape. And so the shape was, we chose Van Gorp's blobby because he showed that this is good for material discrimination rather than a sphere. And in fact, we did a pilot study, tried a sphere. The sphere wasn't very good. The blobby worked better for us. And finally, for lighting, based actually on Roland's work and Paul de Bebek, we knew that we needed to get an environment map to get natural illumination in there. Now, we actually tried to get the workers to go and annotate the image and bring out lighting information. That didn't work very well for us. We did not succeed in that path. We pulled the plug on that, and we just picked one environment map and used it everywhere. This is something we might want to revisit. I think it's a rich area, but this is what we did, and it worked pretty well. So that's what you'd get then. You'd get that blobby with the environment map on it, and the worker spinning around trying to match both the C and the D parameters of the word model to match the tile. One thing I should mention is we found that having context makes a big difference for gloss. You cannot assume that you'll get a specular highlight in that little segment that you happen to get out. But some part of that, a larger object, or if you're in a kitchen with lots of wood cabinets, some of the wood cabinets will get specular highlights, and people will actually use that even though the particular segmentation you're doing doesn't have a highlight visible in it. So that's a case where actually having the context helped us do better in terms of recognizing the material's correct properties. Okay, one thing also, and this is going to be a theme, the right thing when you're doing crowdsourcing is to figure out the right combination of computation and human input. There are things that we humans are terrible at, and there are things that the computer is terrible at. So here's an example. We thought they'd have no trouble with diffuse color. They were absolutely terrible at picking colors. They'd land up at some place, and they'd wander around in the wrong part of this color for a long, long time. So we had to help them. So we added KNN clustering to help them, just a 4-color cluster start off, or let them click on an image. And once they do that, then they're able to be much more accurate. And then they were really accurate on the color, and they could spend more time on the gloss parameters. So that's annotating reflectance. The last stage of the pipeline is getting texture information, and particularly to rectify the texture. So first you need to check if it's a planar object, and then you need to label the surface normal so that you can rectify it automatically. And of course, everything has a correctness test to it. So here's an example of what you would want to do. If somebody segmented this floor, and this is the kind of information you have with annotations in that current image, for the carpet, you would like the user to go in and give you an annotation of here's the normal, and here's sort of the perspective grid that's sitting flat, flush with the floor. And once you know that, you can rectify the texture using a homography to achieve something like this, okay? So that's what we wanted to do, and the first thing we did is we went to gauge figures because people have shown that gauge figures work well. It turns out we actually did a study. The gauge figures didn't work as well as giving them a perspective grid, we found. And so based on a pilot study, we switched to the perspective grid, and that helped a lot. It helped a lot in decreasing their variance. It still did not actually get them to be accurate. People are pretty good at getting close to the right solution, but they don't get all the way to the right solution. And this is another example where you have to add the right computer vision algorithm in. So for example, in this case, we used, and the slide would have said rectification using vanishing points. We used vanishing points, automatic detection of vanishing points in the images. And then when the worker is moving the grid around, when they get close, we snap it to the right vanishing point. So that clears any subsequent error that there is and makes it very accurate. And so that was your original submission. It's not bad when they started off. But then when you use vanishing points, you can see on the right, the lines are parallel. All of them get much better. Okay? So that's that part of the pipeline. And so this is all of it put together now in one. So there's a bunch of stuff. And I should say that any one of these pieces, we had to explore a bit and do quite a bit of experimentation before we got it to the point where it was giving us good quality and reliable data and playing around with different things. But here's what we do. You categorize your scene, you segment it, you white balance, you get the names. And actually, I should say naming segmentation people are very good at. The rectification and the reflectance information are the ones that they struggle with the most, and so we have to spend a little more time there. On average, we had about 43 workers per surface, and if you do the right combination of computer vision, computer graphics algorithms, the right interface, then you can bring the cost down, and we started off at about $2.50 per surface. You can bring the cost down to 13 cents, which is about 13 yen per surface. So this is very, very affordable, lets us get to hundreds of thousands of surfaces. We had a budget of $10,000. We said, we're going to throw $10,000 at this problem, and then we're going to see how far we get. And so what I'm going to show you is what you can get with about throwing that amount of money at the problem. As I said, in all of this is folded, there's verification in multiple stages. We use the work from Perona's group on modeling the bias and competence of workers. It's called the QMAP model, and we use that to improve how we find whether or not the workers are doing a good job. I won't talk about that in detail, but I'm happy to chat later about that. So here's our final database to give you an idea where we are. 110,000 segmentations, so you can see some idea of segmentations here. Here are various fabrics out here. This is shirts. Some are more recognizable than others without the context. And I'll show you sort of a little more detail on them. This is what people actually produce. So here's a nice one. This is a wall, and they've taken everything out that is in the wall. And you can see they've taken out the outlets, they've taken out the lamp, etc. And they've left exactly what they were supposed to do, one material segment, which is the wall. This is the faucet, it's all metal, and so they pull that out. And so you can see there's a lot of detail that we were able to get out from them. Here are some more examples. On the top are the segmentations, and on the bottom is the context. I remain baffled at how detailed they were willing to go. This is 13 cents for the whole segmentation, and all of the cost was in the texture and the reflectance. So they were doing this for 1 or 2 pennies, this kind of segmentation quality, which I remain shocked by. And I think, therefore, that this part can be made into a game, since they actually seem to be having fun with it. So we may as well do that. And so here are more detailed ones. You can see that they've captured, and they're doing the right thing, which is capturing materials and not object segmentation. We had to train them on that. Their natural instinct is to do object segmentation. We had to train them to do material segmentation. And here's a dog, and they correctly remove the nose because the nose is not made of fur, and therefore it is a different material. The dog's eyes are closed, so they left the dog's eyes alone. So this is some idea of the material segmentations we get. We have about 25,000 textures right now. And here are examples, and you can see on the left is a source photo, on the right is a rectified texture, and it's doing, you can see it's pretty parallel, it looks pretty good, looks like it's rectified. Same here, these are ugly images, but they show you that the rectification works, so. And then finally, we had about 50,000 reflectances. And so I'm going to show them with these blobbies, and I'll show you first shiny materials and then more diffuse materials. In the shiny materials, you can do the metals, like the one on the top. You can also do ceramics. So this is the match that people have achieved. They're doing it with a different lighting, but they're still pretty happy at doing a reasonable job of capturing it. Here are others. Again, on the top are some metals, and on the bottom is a ceramic bowl. And finally, here are sort of non-glossy, more diffuse types of materials like fabrics and walls. And you can go online and browse it. And in fact, here's sort of what you would see if you were to go to our website and browse it. We have about 20,000 wood examples of 14,000 fabrics, 10,000 metals, 2,000 granite. I'm a little behind leather, food, etc. Some categories we got which we didn't expect. In fact, I thought we would eliminate faces, and people went nuts on faces. They like segmenting hair. So we have hair segmentations. I'm not sure what we'll do with it, but it's there in the database. If you have an idea of what to do with it, go, run with it. Object names was more a bigger set. Materials, we have about 34, and we would let them pick walls, floors, pillows, chairs, the usual stuff, doors, etc. All right. I'll let you see that. But you can go online and browse it, and it's all there, so it's easy to play with it. Once you have this information, you can do some nice things. Thank you. You can do things like search for a wooden floor that's shiny. And that's actually kind of nice. So people have not been able to actually search on a shiny wooden floor. You can try to search on a wood floor and hope that people annotate it textually correctly, but this is actually able to do that based on the parameters that we've collected on gloss. And this is now searching on faucets, which are based on color matches, etc. And you can search for more metallic things and other such things. Okay, so the title now says sort of a summary. And so this is a summary of this part of the talk. So it's a public, browsable, searchable, 100,000 material database. That's the website, and you can go and run with it. We've actually also posted our code there. So if you want to run tasks yourself using our code, you're welcome to do so. When we first started, we weren't sure that we could get good data and that crowdsourcing was going to give you reasonable material data. And we feel pretty good that actually that is possible. It's possible to scale and get verifiable, pretty good quality results out of this process. So that was good. We had this data. But there's still one thing that's not quite right, and the title should say intrinsic images. These material segmentations have shading that is baked in with the material, right? So this is this famous characterization of the problem. I is equal to R times S. I is the image, and that's basically measuring reflectance times shading. At this point, we're assuming diffuse reflectance. We're not actually, we meant to talk about gloss at this point. It got too hard in our model. We just decided to initially focus on just diffuse reflectance. And in our database, this means that when you have images that are shown like this, that's the I, which is the image for particular segmentations of a shirt or of this bed cover. Then you want to split it into R and S in this way. You want to get the shading out so that you have the real clean material. From open surfaces, we're doing okay on these homogeneous materials like the shirt. But the textured material, we have a texture with lighting all baked inside, and we have no easy way of separating that out. So the first thing we did is we said, okay, we need to solve this problem. How about we run, there are lots of great intrinsic image algorithms out there. Let's run them on this, and let's see where we land. We ran them on this. We landed somewhere. We had no idea how to characterize where we landed, because there is no way to judge the quality of whether or not this is a good intrinsic image decomposition. So that led to this next project that's going to be presented at SIGGRAPH next month. So again, these are materials that are in the wild, so there is no data to tell you whether whatever you got back is actually a good material value, and we don't have ground truth. So we realized we needed to go back, because we actually had some confidence now we could get crowdsourcing to give us good material information. We had to go back and collect human annotations of reflectance comparisons. Okay, so that was sort of the key insight, the key problem that we needed to solve in this project. And so then we had to step back and think about, well, how would I go and do that? So what we did is we took images. These are actually our open surfaces images. And what we did is we found out pairs of points there, and we sent it to a crowdsourcing, again, to Mechanical Turk pipeline, and we got pairwise material annotations. So people will tell you how to compare 2 points or the materials at those 2 points. That's a bit vague, so I'll tell you a little more about what we actually did. So the first question to ask is, what judgments should we collect is the title of the slide. So what should we ask humans to do? Humans aren't very good at absolute values in images. They aren't very good at illumination. We've played a lot with illumination, and they're not very good at it. They are better, still not very good, but they are better at judging relative surface reflectance. And so the question we decided to pose, we went through multiple questions, we also ran some pilot studies. The question we posed was, which point has a darker surface color? So we give them 2 points, and we spend a bunch of time explaining to them that the point, the intensity of the pixel may be darker in one, but the point might still be a brighter surface color, right? That was a tough thing trying to get them, and this one has a very extensive training section, which we posted on our website, so you can see how we trained our workers. So here are the points. So first we take images, and then we do a Delaunay triangulation and pick some radius of the image and pick a bunch of points. And what we do is we pick pairs of these points and ask the workers to answer which point has the darker surface color, okay? So first thing, of course, you quickly realize that you need to throw out some points that it's not clear what you're really asking them, and they certainly have no idea, even when you're very clear about what you're asking them. So you remove mirror surfaces and transparent surfaces, because they just confuse everything. So that was an easy part. You remove difficult points like this. And then task 2 is you have which point has the darker color, and we gave them a tutorial. So we would show them 2 points, 1 and 2, and you can go online and again see the demo. You have to have the points really jump out at you, so we had to do a bunch of user interface work to make this all work well so that they could see the points even. And we say point 1 and 2, which one is darker? We gave them an extensive tutorial. Without the tutorial, only half of them understand it. With the tutorial, 30% still don't understand it. So this is not great numbers. We aren't thrilled about it, but this is a hard question, and that's just what I think what you're going to get. We ran pretty big studies on this, essentially. We included sentinel tasks, so there will be tests that if they fail, we don't immediately throw them out. We even pay them and thank them and all that stuff, but we never accept them for our jobs again. And after we did all this, we arrived, and this shows you again that result I showed earlier, except now we're ready to understand it. Here's the kind of annotations we got. So first, as I said, is we wanted to do this for a large set of images in the wild. We didn't want only a small database of 10 images or 20 images or even 100 images. So the big data set is 5,000 sparsely annotated images. Additionally, firstly to validate whether we were doing the right thing, and in cases where you need higher density, we also have a set of 300 densely annotated images. So the left is how the sparse annotation looks. We've picked a few sets of points, about 100 points per image, 100 pairs per image, and on the right is the densely annotated images. Okay. In total, we have 5.4 million judgments, and now to understand how the judgments are, you can look at the legend on the bottom right. So if 2 points have about the same reflectance, then they're connected by a bar that is of equal thickness. And if point 1 is darker, then it's got the little the small end of that little less than sign. And additionally, the confidence of the worker using the QBAM metric is shown. Blue is more confident, orange is less confident. So you can see that actually, if I'll just now show you this little rectangle here, you can actually see pairs of points that are on the wall are correctly being determined with high confidence as being equal reflectance. Points that have the floor and the wall are correctly being determined, again with high confidence, that the floor is darker than the wall. And so there's 5 million of these, and we've actually posted all the data online. Again, you're welcome to go and look at it, but the people seem to do a pretty good job. So then we ran all the existing algorithms that are there for intrinsic decomposition, and it turns out that they're, well, as I said, we didn't know if they were working. We figured out one problem that they seem to be failing on. All of them assume local constraints. They look at local neighborhoods, but therefore they cannot catch a link like that wall and that wall are the same color. We all know that. I mean, you're going to look at it and I tell you, and of course you buy it, that wall and that wall are the same paint, but that requires a very different dense CRF formulation, which has typically been hard to do. So we used a dense CRI formulation using other sort of technology that's out there and devised an algorithm. I won't give you the details of this algorithm, it's in the paper. But I want to tell you that it seems to work better right now than all the other algorithms that are out there. None of them work terribly well is also an important thing to note. And so I think this is an important area we need to work on. So what do I mean by it seems to work better? So we had to come up with some way of characterizing the quality. And the characterization we used is a fraction of the judgments that an algorithm disagrees with the worker annotations. And it's weighted by the confidence of the annotation. So that's the measure we use, and again, this is all posted online, and we've even posted all the different implementations and our implementation of the algorithm so people can build on it and hopefully improve it, because 21% error is still pretty high error in algorithms, even if it is the best we can do. All right, so to quickly summarize this part of the talk, thanks to crowdsourcing and photo collections, we really do have access to a wealth of information out there. And with crowdsourcing, we can get perceptual data. The fear has always been that maybe the quality of this data is a bit dodgy, but there are ways to get good data out, and that's, I think, really a wonderful thing to be able to do, because you can really scale. And in the future, we want to build intelligent material-based search, material recognition algorithms, et cetera. Both of these data sets are out there. For the intrinsic images, we've put the annotations in the code, et cetera. I'm actually going to take 5 more minutes. And this is the open surfaces data. So that's the first part of the talk. If I have a few more minutes, I want to talk about 2 questions. And I want to give 2 slides per question, which I think Ted was supposed to talk about it, but Ted says now he's not going to talk about it, so I'll throw it out there. OK, so this database stuff is looking very much at computer vision, taking images and trying to see what we can get out of images about materials. The other side of it is how do computer graphics people model these materials so that you can produce images that are indistinguishable from reality? That's the hope, right? We want it to be indistinguishable. So I'm going to talk very quickly about 2 projects we did. One was, the question was simple: what makes white jade look like white jade? And the second, another simple question: what makes silk or velvet look like silk or velvet? Okay? So for white, and I'll try to give you a quick pithy answer in 2 slides for each. So for white jade, here's an example that was an inspiration to us. This is a Chinese emperor's seal. And computer graphics does a pretty good job of producing the base, which kind of looks like marble and is very diffusive, and we have great algorithms for that. But the exquisite detail of the dragon, with its thin, translucent, glassy appearance, was not actually achievable before we started looking at this problem. And the answer as to what makes white jade look like, I'll give you the punchline right now, is something called the phase function. So the phase function does is it decides how, when light enters a medium, where does it scatter? It's just a probability distribution function that you'll scatter to the right, left, front, back, etc. Okay, that's the phase function. So Ted, in his basement, I think, we can't afford white jade. We've discussed it. Ted says it costs, it's more expensive than gold. So we can't afford jade at all. So Ted in his basement has been mixing waxes and soap. And he mixed this particular kind of wax and shone a laser at it and produced images that look like this of the light shining on the material. On the top is what I call a teardrop shape. It's very classic, and a lot of materials have that. On the bottom is what we call an apple shape. The light comes in and kind of turns around. And that apple shape is harder to get. So existing models basically do a good job of producing teardrops, whether you have an apple or not. And we were looking at this problem, and we were quite disturbed by this lack of fidelity. And that led us to basically looking at the phase function and characterizing, adding an extra dimension. So we tried to find the perceptual dimensions of the phase function, and there was this old diffusive dimension down here, and we added this orthogonal dimension of glassiness, which people hadn't talked about before. And that, as you can see in the red bars on the right, shows that you can actually fit that apple shape rather than only producing teardrops. Based on this idea that phase functions are important, we then went on to measure materials that have these kinds of properties. And this, I think this is probably the best looking soap there is out there. So we're quite proud of it. I know it's only soap, but it means a lot to us. And we correctly capture, if you look at the sharp corners of the soap, it correctly looks like it should, which you wouldn't get right if you use the old phase function models. So that was the one quick project I wanted to talk about. The second quick project I wanted to talk about is what makes silk or velvet look like silk or velvet. And the answer is the structure of the material, for the most part, determines how it looks. So how do you get to the structure? So what we've done is we've designed a pipeline where you take micro-CT data. Micro-CT data gives you micron resolution data for velvet and silk, and here's what you get if you do that. We are sweeping from the top of the velvet down to the base of the velvet, and as you go on the right, you see a 3D visualization. In the middle, you're seeing the scan slices. I'll show that again because it went by quickly. As you go from the tips down, you see that velvet pokes up, right? The fibers poke up, and there's this matted bottom area that is the substrate. Silk, very different appearance. So let's go to silk. Whoops, sorry. Let's try that. So silk is very tightly interwoven fibers that you can just see the structure of right there, and it's flat compared to the velvet. So once you get micro-CT data, you have no optical information at all. We took one photograph and computed 2 metrics on the photograph, added that in, and we could produce models that look like silk or velvet. So what are the 2 metrics we compute on the photographs? They weren't terribly exciting, unfortunately, just the mean and the standard deviation. But what was important is what optical property do you couple it to? So we have a whole model for the scattering of light in such media, et cetera. And you match the mean to some idea of the volume albedo. So you model the material as a volume, and you have a single scattering albedo. And you match the standard deviation to some idea of the gloss or the spread of the particles that are in the volume. That's a very, very broad way of describing it. But if you do that match, you can then produce silk that looks like this. So this is virtual silk. Don't get scared by the numbers. We improve performance. But hopefully you agree that it has silk-like properties in its appearance. And here's velvet, and you can see that characteristic reflections and the asperity, so to speak, at the rim of velvet, because that's what makes that, the fibers poking out, getting that right makes velvet look right, basically. And that's it. So I want to give credit to the people who do all the work. So these are the students. Sean did open surfaces and intrinsic images. Shuang did the cloth work, and Yanis Galakis did the scattering work. And with that, thank you. And stop. I'm sorry I'm late.
Thank you. So, I don't want to stop, but anyway, okay. We have only 3 minutes. Okay, roll on. So, can you use the microphone?
I got a couple of quick questions. Absolutely beautiful renderings at the end. It wasn't quite clear. So the geometry was that you showed at the end. That's captured geometry? Or is that a resynthesis based on statistical parameters derived from the geometry?
So this geometry?
Yeah.
So this is synthesized volume data. So we take CT scans, we compute volumes from it, and then we synthesize large swaths of it using a texture synthesis algorithm that we came up with.
Interesting. Yeah.
But then the optical properties come from the match of that mean and albedo.
Right. Okay. I also had another very quick question, sorry, and then I'll hand over to someone else. Could you just say a little bit more about how you do the verification with the crowdsourcing stuff? So how do you work out whether people are saying the right thing or not?
Right, so you actually send it to multiple people to verify, and they all need to agree. And we used initially majority voting to then pick. But then if you use QBAM basically tries to, over time, build up a model of the bias and the competence of different workers, and then you can use that to do a better job of pruning bad data.
So I have sort of a question and a comment. So in your reflectance mapping, or whatever you want to call it, you're essentially brainwashing your people into thinking that surfaces have uniform reflectances and everything else is, and people don't do that normally. So
I don't have to work hard to brainwash. You mean they give us a segmentation, and we say, pick a color that best represents it. In the case where it's a textured, very richly textured material.
No, I'm talking about the place where you had the 3D scene and you had the wall with a curve and then you had a corner and it was darker in the corner and you're telling them, well, this is not darker than this is the same thing.
Oh.
Essentially you're brainwashing them to to assume that these surfaces are the same.
Right. So you're relying on them believing that if you haven't painted the room in stripes to be dark and light, but actually if it's a wall of the same color. That's what that's your question?
Yeah.
That is correct. So you're relying on that, and so.
But you don't know that either.
That's right. But on the other hand, on Flickr, the people are boring and they post boring. They put, that match all these priors and expectations, right? It's not the optical illusion Flickr. It's here's my kitchen with my cat in it, and it's always got a cat in it, right? So that's you're relying on sort of the normal world has certain behavior.
Right, so I'll give a 10-second comment.
Yeah.
So my experience with the gauge figure thing is it really flattens out volumetric appearances. And the way you can test this is if you give somebody something volumetric and have them set all the gauge figures, and then give them a side view, which you make broader or stuff, you will see that their gauge figure estimate does not fit what their visualization was of how deep the thing is. Yeah, I know, in this particular one,
right.
But I mean, if they ever expand it.
Right, so if we expand it out, but then that means I shouldn't use gauge figures
no,
still.
You shouldn't.
Right, so we already
or
got that to a different
Or if you
path.
use them, you can turn the scene around and have them double check.
So see multiple views of it. Yeah. That's fine.
Sorry, I got to jump in on a comment on this. So we had big problems with this. All you have to do is train them. All you have to do is teach them that if they see the surface, you have to teach them how to do it. If you see the surface as curving out to the line of sight, then by definition the gauge figure has to be absolutely along the line of sight. And once they've understood that, then the volume comes straight back into all of their settings.
Okay, thank you very much.